And yes, Gordon, you changed your name. You're no longer youthful. You're back with the rest of us.
Yeah, I accepted that a long time ago.
Yeah.
I am recording now, so if
Okay.
you don't want to be recorded, bail out now.
Okay.
Take it away, Dan.
Okay, thanks. So welcome everybody to the Marine Amateur Radio Club first Thursday club meeting of September. It is September 3rd. Last time we met, we talked about EMPs and CMEs, the differences between the two. And towards the end of the presentation, I alluded to the fact that we were going to talk about how to protect ourselves against EMPs. And so this presentation is about Faraday cages that work. And so without further ado, I am going to, first of all, I need to share my screen. So let's share the screen. And let's click on Start Presentation. And I need to swap Presenter View. Okay. Does everybody see Faraday cages that work?
Yep, looks good.
Oh,
Yes.
okay,
Yes.
great. Perfect. So we're going to talk about Faraday cages, how they work against EMPs, and you're going to learn why they work. So to introduce this, we're going to first summarize what an EMP is and how it affects electronics. Once we understand what an EMP is, then we can understand how to create a Faraday cage. The problem that people have on the internet is they do not understand EMPs. And so without understanding what you're trying to protect against, you'll never get it right. And that typically is what you see on the internet. A proper Faraday cage can be built. It is possible. As a matter of fact, nowadays we've come a long way in protecting against EMPs. The information that I am presenting was provided by a gentleman that I studied with at length. His name is J.T. Smith, and this is from a paper that he created in September 20th, 2014. So it's out there on the web. You have to know how to find it. And I have the actual report that anybody that for my source material that I will send out if anybody would like that. So let's quickly review what an EMP is. An EMP is electromagnetic pulse caused by a detonated nuclear weapon. A high altitude EMP is similar, but it's detonated in the high altitude. It's very, very simple. There are three parts to an EMP. There are three pulses, an E1 pulse, E2 pulse, and the E3 pulse. This graph here, as we saw in the other presentation, shows you the times and the strength of each of the pulses, the induced voltage amplitude per meter versus time in seconds. First is the E1 pulse. This, of course, is the most powerful pulse. It's the thing that's the killer. Whether you're connected to the grid or not, it does not care. What happened? Okay. The wave pulse has an extremely rise time of 5 nanoseconds, and it doesn't last very long, mid-level decay of 150 nanoseconds. And nanoseconds is, of course, a billionth of a second. It can induce up to 50,000 volts per meter on electrically conductive material at ground level. And it is the pulse that the Faraday cage needs to protect against. Because of the fast rise time of the E1 pulse, the physical length and electrical conductivity of the target equipment determine the voltage level that could be inducted into the equipment. For example, without shielding, a simple 6-foot electrical cord could receive up to 100,000 volts on it by such a pulse. 6 feet is roughly 2 meters, 50,000 volts per meter times 2, that's 100,000 volts. A 4-inch cell phone could receive as much as a 5,000 volt pulse. And this E1 pulse is too fast for normal commercial transient spike protectors to handle. Although I will say that there is a new company out there that actually has a transformer. It's like a $300 unit that you put on your electrical panel that is supposed to protect your entire house because it is very quick. It understands what an E1 pulse is, and it clamps down on the, it shorts out, if you will, in billionths of a second. And I'm talking like 1 or 2 nanoseconds. So it is very, very quick. We'll talk about that more later on. The initial part of the E2 pulse, speaking about the E2 pulse, is that it overlaps the E1 and it resembles a lightning strike and can last up to 2 seconds. It can induce about 100 volts per meter in conductive material. Because of the similarities to lightning cause pulses, and the widespread use of lightning protection technology, the E2 pulse is generally considered to be easiest to protect against. But here's the problem. The main potential problem with the E2 component is the fact that it immediately follows the E1 component, which typically will destroy whatever it is that you're trying to protect. I'm talking about the surge suppression devices. They get fried with the E1, leaving the E2 pulse readily available. Okay, so then the last one is the E3 pulse. This is the late time wave. It can last several minutes. This surge can affect electrical equipment if connected to the power grid. The E-pulse is the same type of pulse where you get a CME from. And because it's a very slow pulse, lasting tens to hundreds of seconds, that is the E3 component of the pulse is a very slow pulse. I ought to just read it. Lasting tens to hundreds of seconds, that is caused by the nuclear detonation, heaving the Earth's magnetic field out of the way. Now, if you go onto the internet and take a look at how the E3, how an EMP works, they have some pretty cool diagrams that show how the Earth's magnetic field is heaved out of the way. So it's worth taking a look at. So knowing what you're up against is paramount in defending against it. So what do we want to do? We want to shield our stuff. So obviously the ideal solution would be to have the entire house shielded. The cost of doing this, however, would be as much as the house itself. For this reason, the goal is to identify critical pieces of equipment. These critical items must remain operable no matter how intense the EMP is and no matter when it occurs. The thing that actually does this is called Faraday cages. These Faraday cages must suppress the strength of the EMP pulse down to a level that the equipment can tolerate. And that's the key to the Faraday cage. It needs to bring that pulse down, bring that 50,000 volts per meter down to 5 volts per meter or less. And so that's what we're trying to do. So how much is enough? And there's only one equation that is used for this, and it's this right here. This SE, which is shielding effectiveness, is expressed in dB, or decibels. And so what we do is we take the amplitude ratio, which is the attenuation of the container, and you put that into this logarithmic equation, and it comes up with a decibel reading of what it's able to do. So example, if the EMP is 50,000 volts per meter and we would like the container to reduce it inside to 5 volts per meter, then the amplitude ratio would be 50,000 divided by 5, which is 10,000. So if you plug that into the equation, you get 80 dB. And actually, this is the golden number that we try to bring all of the Faraday cages to. If your Faraday cage will attenuate by 80 dB the pulse coming in, you're going to be safe. So here's a list, or here's a table that we talked about actually last time we were here, I believe. There's the 80 dB goal. The amplitude ratio is 10,000. It reduces it to 5 volts per meter. Volts per foot is 1.52. Volts per inch is 0.127 volts. And any cell phone can withstand that. That is a piece of cake. As a matter of fact, it could probably stand a 65 dB amount. Well, at least a 70 anyway. So we may come back to this table because some of this presentation talks about it. So as an example, let's take, I have like 3 examples here. If a 4-inch cell phone is placed in a container which only has a 30 dB of shielding effectiveness, then the phone would receive an induced voltage equal to 160.8 volts. How do we get that? Well, 40.2 volts per inch times 4 inches. The 40.2 volts per inch is 30 dB. So let's go back to here. We see 30 dB. There's 40.2 volts per inch, which is 482 volts per foot. So that's how we get the 160.8 volts. And obviously, what will happen if you submit a phone to 160 volts? Well, the phone no longer works. It is fried. Phones are good for, I guess, about 10 volts. So, of course, that would instantly be destroyed. Let's go to example number 2. This is a hand drill with the power cord wrapped around it. And this is very important. The cords that you have on your devices act as antennas. And so if you have the cord wrapped up, then it's not going to act as an antenna. So if you place this power drill in the same container, then it would receive a pulse equal to 482 volts, which is 482 volts per foot times 1 foot long, which is 482. And we know that this is from a 30 dB. We're using the same container, so 482 volts using a 30 dB attenuation. So the question is, will it work? It probably will survive because some drills are good for 600 volts. It can withstand a spike of 600 volts. So 482 volts, it'll probably work okay. So what happens if you take the same drill with a 7-foot cord and the cord is not wrapped up? Well, you're talking 3,800 volts at that point, in which case it would damage the drill more than likely. Example 4, using the same drill with the cord wrapped around it. It's placed in a 55-gallon barrel with a 76 dB suppression. The pulse, the drill would see 1.5 to 4.82 volts, well within the rating of the device, so that would be just hanky-dory. So there are a few things that make building a Faraday cage very important. The size, the type of equipment, and the container suppression levels. Those three things are very, very important. As a matter of fact, they're critical. And there's one thing that I actually forgot, not only the size and type of equipment, and not only the container suppression level, but also there's a insulation material that we need to take into account. And we're going to talk about that a little bit later on. But there's actually 4 parameters that must be taken into account to ensure the protection of the equipment. Did someone have a question?
Dan?
Yes.
You enlarged the type on it. It's hard to get it on the screen now.
I'm sorry?
The type looks like it was enlarged just in the last minute or so. So I can't see it as well on the screen.
Does everybody
same.
see?
Looks the same from here.
It's that fine.
Oh, okay. I must have done something. Excuse me.
Maybe drop out of the chat of the Zoom and then come back in. Ragnar, you might be okay.
Yeah.
I fixed it. Thank you. Sorry.
Okay. One thing that is also important to understand is if an object is placed in multiple containers, then the resulting protection is the sum of the suppression of each container. So if you have a 30 dB attenuation container inside of a 80 dB, then you would augment the 80 dB by 30 dB. So that's good to know. Well, the above examples consider EMPs of 50,000 volts per meter. Several of our enemies have announced super EMPs capable of producing 200,000 volts per meter. So, you know, the military, their standard is 50,000 volts per meter. So when they create a Faraday cage, it's based on a mil spec of 50,000 volts per meter. But just know that that might not be enough if you're protecting just against 50,000. So that's why I like this second point here. You're able to use multiple containers, put your most valuable equipment in multiple containers so that you can it can withstand a 200,000 volt per meter EMP pulse. Okay, so that's basically what I said here. So let's talk about how Faraday cage shields work. The whole issue with shielding comes down to the size of the hole, pun intended. The EMP pulse shielding requires the equipment to be surrounded by a continuous electrical conducting metallic container with very few, if any, holes, and the size of the holes matters. For example, a container consisting of a 1 mil thick aluminum foil can provide up to 94 dB suppression, provided that there are no holes allowing leakage. So having a 1 mil thick aluminum foil, which is your standard aluminum foil that you use in your house, actually, if you create a box with no holes, that will produce a 94 dB suppression. The amount of leakage of energy into the container is determined by the signal wavelength and the relative size of the holes in the shield. So the sum and size and number of holes in the shield must be hundreds of times smaller than the wavelength of the signal in order to suppress an E1 pulse sufficiently to protect the equipment inside. And so we're going to have an example here. Guess what this is? Yes, a microwave oven. This whole thing can be understood by examining the glass door of a microwave oven. The door window contains about 50 holes per square inch. Each of these holes have a diameter of about 1.2 millimeters. And we're going to discover why you don't get zapped when you turn on the microwave oven. Table 2 in the next slide indicates why visible light can easily pass through the screen door with very little, with their very short wavelength. The wavelength of visible light is 0.38 millimeters. The frequency of visible light at the violet stage is 789 gigahertz. So the ratio of the wavelength to the oven hole size is 0.317. And that'll make more sense when you see the next slide, which is this here. So here's the microwave oven. The frequency of the microwave is 2.45 gigahertz. Look at the frequency of visible light, 789, and that's on the violet end, 789 gigahertz. And look at the microwave oven to the wavelengths. There's a frequency of 2.45 gigahertz, the ratio of 100. That's why if you put your cordless phone in there, your cell phone or FM radio or AM radio, the more than likely, especially on the cell phone and the FM and AM radio, and as a matter of fact, on the internet, people prove that the microwave is a good EMP protection because they put their AM or FM radio in there or their cell phone. They try to make a call and it does not work. Why? Well, because of this right here. The actual holes do not allow that frequency to pass through readily. But the problem is the E1 pulse is at this cordless phone frequency, and it can pass through. We're going to have an example a little bit later on. So, how much shielding is required? The above table shows that in order to determine the signal suppression of a Faraday cage, it is necessary to examine the effective frequency and wavelength of the signals versus the size and quantity of holes which allow leakage. In other words, the size of the holes, the frequency of the pulse, and the quantity of the holes which allow leakage will determine the effectiveness of the Faraday cage. The military has defined the minimum dB shielding required at different frequencies, and the following diagram shows this. So here's the shielding effectiveness on the left-hand side, the SE in decibels. There's our magic 80. You'll notice that the AM radio and the FM frequency, they can easily, if you don't have it at 80 decibels, they'll easily pass through that. Here's various things, various Faraday cages, and we're going to talk about each one of these and why they're able to have a shielding effectiveness of what they show here. So this is actually a pretty good diagram to refer to. And this is the mill standard 183-125. There's a few warnings that we're going to see during this presentation. Warning number 1, several persons have posted videos on the internet demonstrating their measurement of metal garbage cans when used as a Faraday cage. They put their AM or FM radio in the metal garbage can, closed the tight-fitting lid, and the radio stops playing. They conclude that they have demonstrated their metal garbage can is a good Faraday cage for EMPs. I'll bet you if I ask for a raise of hand, people will have seen on YouTube people demonstrating this. Well, the problem is that's not so. The frequencies we're dealing with are not the same frequencies of the AM or FM radio. And so this is why their garbage can will be worthless in protecting against the higher EMP frequencies in the range of 10 megahertz to 1 gigahertz. and as a result, the contents inside will be fried by any typical EMP. There's good news, however. The good news is that their destroyed devices will already be in the garbage can, because if they are protecting against E1, which is 10 megahertz to 1 gigahertz, it's not going to do it. There is a way to make your garbage can up to an 80 dB Faraday cage, and we're going to talk about that. But just the way that they show on the internet, buyer beware. I alluded to insulation at a previous slide when I talked about 3 things that are necessary. The 4th thing is this insulation, and we're going to talk about that right now. So you need to understand that an EMP will induce a 50,000 volt per meter on the walls of the container. Okay, so an EMP happens. You have your garbage can. It's let's say it's a 1 meter high. So on the skin of the garbage can will be 50,000 volts. And that can be felt on the inside of the garbage can too. This is why you need insulation. Referring back to table 1, the container that has 80 dB of shielding, the contents inside would remain at 5 volts per meter. So if that same garbage can properly insulated, or properly with all the holes filled out or covered, if it has 80 dB of shielding, then inside would remain at the 5 volts per meter. The skin, however, is still 50,000 volts per meter. So we need to protect ourselves against that. There's a 45,000 volt per meter difference between the two. Remember this. Typically, a difference of 10,000 to 30,000 volts can arc across 1 inch of an air gap, depending on air pressure, particulate content, and humidity. A difference of 3,000 volts can arc between 2 items when separated by 5 millimeters. So you can get a 5,000 volt can arc between a gap of 0.2 inches is what I'm trying to say here. So insulation is very important. The internal contents must be surrounded by a seamless anti-static or other very high resistant material to prevent arcing between the container wall and that device. So I think I may have misspoke. The outside of the container is 50,000 volts per meter. The inside skin is 5 volts per meter. I think that's what that means. So the lid need not be insulated provided there are at least 2 inches of space between the equipment and the container lid. If, however, the container is filled towards the top, the lid must be also isolated from the contents inside. And anti-static pail and drum liners made of high-density polyethylene, 15 to 24 mils thick, and having a resistance of a 10 to 11 ohms per square are available. And all of this stuff that I talk about, again, is in the report. JT actually tells you where to buy this stuff. So I'm just giving you a highlight of what he was talking about. Go ahead.
So conceivably, if you had your 1 meter high aluminum garbage can and you built a lid structure inside it that kept your equipment 2 inches off of the floor of the can and at least 2 inches away from the inside of the can and 2 inches from the top, then you'd probably be fine because the wood is such a poor conductor. Or would you need to use something like glass for 50,000 volts? I don't know if wood.
No, because on the inside is 5,000.
It's lower. Okay.
Yeah. So I misspoke. The difference is that 45,000 volts, and that's what we're trying to protect against. And so having a wooden container, and the important thing is it has to be absolutely seamless. If you have, if it's a box that you're putting it in, and you have it glued, and there is a millimeter hole between the two edges, that will destroy the effectiveness of that box. Okay, the holes are very important to not have. So that's why you dovetail things, so that makes it very difficult for holes to exist in joints. As a matter of fact, we're going to talk about some of the issues with that. So speaking of which, on the internet, you constantly see people using simple cardboard as an insulation between the container wall and the contents. Cardboard insulation is not much better than air, which is obviously insufficient when one considers the high voltages. Also, during using these materials, the container floor lid, wall coverings are separate pieces of cardboard, which means they're not joined, which means that there is air spaces between the seams. They don't use a single continuous high resistant barrier. So in other words, the electronic equipment will likely be destroyed by any high voltage EMP. So moral of this story, do not use cardboard. And you see that on YouTube all over the place. Okay, so practical considerations for Faraday cages. And there's a couple of slides here that actually talk about things that we're trying to do. So we want to have a solid metal container with virtually no holes. Any and all holes in the metal shield must be covered with a conductive material such as aluminum foil tape. If it will hold water in any position, it will also hold out most EMP wave energy. That's your litmus test. When you create your EMP Faraday cage, to test if you have any leaks, i.e. if there is small holes in there, if it's leaking, then if water can come out, then EMP energy can go in. A note about aluminum tape. Most aluminum tapes in hardware stores are either too narrow, too thin, too weak, or they are so sticky that it's impossible to remove without the use of a razor. Using the wrong type of tape, you'll spend hours removing it before the container can be resealed. So the type of aluminum tape is also very important to use. Other practical considerations, talking about aluminum tape, the Ideal Seal 2000 or the 758AB from Ideal Tape Company is what the author uses, what JT uses. It's 2.5 inch wide. I've seen it in use, and this is right on. It's strong, it sticks well, and it comes off cleanly. So if you're going to use a tape, this is the tape to use. If your equipment is used frequently, then the container must be easily opened. So you're probably not going to be using tape for those type of devices. The containers that use the tape will probably be for devices that you do not use a whole lot, because you need to, each time you open the container and close it, it needs to maintain the level of EMP suppression. If it's not easily opened or closed, then you're going to have issues by keeping the protective container intact. The equipment not essential for, let's see. Okay, this equipment is not essential for equipment being put into long-term storage. So again, we're talking about something that is taped up that you only will use maybe as needed. You put that in something that you can tape up. Okay, let's see. There's containers of different sizes and shapes are required because you have different size and shapes of your equipment. Electronic equipment containing microchips must they're a lot more sensitive, which means they need the 80 dB suppression versus electric motors. Electric motors can handle a 600 volt shock most times versus a CPU or some small transistor, which is in every device that we have, electronical device, I should say. The containers must be rugged enough that they will not become ineffective when handled roughly. And that comes into play because when if an EMP ever hits, society will come to a halt, and you'll be throwing around your Faraday cages quite a bit because you're probably not going to be staying in place at your home, depending on how the civil unrest happens. That's a whole nother presentation. Or you could just, and I refer to this in the first presentation, read 1 second after, and it'll kind of give you an idea of what society will do during an EMP attack. All items stored within the container must be electronically insulated from the container's lid, walls, and bottom. The containers and associated liners must be readily available and inexpensive to purchase. Again, these are all practical considerations for creating your Faraday cage. And here's something very important. Do not ground the container, your Faraday cage, to earth ground, because the grounding cable will appear as an antenna. You do not want antennas with the EMP pulse. You notice that the airplanes, they're nothing but a metal hull. They have no grounding, and they're always hit by lightning. So you do not need to ground it. As a matter of fact, you do not want to ground your Faraday cages. So let's talk about various container types. And I'm going to go pretty quick because I'm just going to highlight some of the things with each slide here. The first one is a 1 gallon metal paint can, paint can with a standard friction lid type. These have a measured signal suppression of 87 dB, which is great. The friction lids are easily opened with a screwdriver and closed with a rubber mallet. They're small for most electronic devices. Their suppression inside should be about 1 volt per meter, which is great for any type of microchip electronic equipment. They're rugged. New paint cans are very inexpensive, and anti-static liner bags are readily available to be used with these cans. So one of the best things you can use as a Faraday cage are these 1 gallon cans. The next one is a 3.5 to 5 gallon Pels with quick release lever lid, and I'm going to show you a picture later on. And these are still steel containers. They still provide 80 dB suppression. The lids are very easy to remove and close, and once you see the quick release lever, you'll see what I'm talking about. They're obviously large enough for larger electronics, even laptops. Their EMP suppression reduces the inside voltage to 2 volts per meter, which is at 3.5, that's 1 volt per meter. So I mean, you're getting plenty of microchip suppression levels with these 3.5 to 5 gallon Pels. They're rugged. They're $5 to $6 each, and they have anti-static Pel liners for these that are 15 mil thick that are available for $2 to $3.
Hey, Dan.
Yes. Yes, sir.
Is that like on the 50,000 volt instead of the 200,000?
These are all
what that's based on?
Yeah, this is all based on 50,000. Yep.
Okay, thank you.
Yep. Okay, then the largest one is a open top steel 55 gallon drum with the same type of quick release lever lock lid. These suppress 76 dB at 1.96 gigahertz. The lids are easy to open and close. These containers are great to put large items in. Plus, you can put in 28 1-gallon cans if additional protection is required. So this is, you need to remember, if I have that 1-gallon paint can that does 80 dB plus the 76 dB, now I can start thinking about being protected from a 200,000 volt per meter pulse. The suppression on these big cans are about 4 volts per meter, which is still sufficient for the microchip electronic equipment. They are rugged. So let's see. Okay, so the next part is talking about the same gallon drums. This is just a continuation of the previous slide. You can find them on KSL for about 20 bucks. Make sure that they're clean, used drums. Anti-static drum liners of 15 to 24 mils are available for $10 to $14 at CDF Corp and other sites on the web. And there's the 55-gallon, there's the 5-gallon, there's the 1-gallon. And you can see these, now that you see these type of lids with the lever, it kind of now makes sense, doesn't it? That's what you're looking for. This is what you want. There's other types of storage that are they don't necessarily meet the mil standard 125, but they can be used if you wrap the edges with the aluminum tape. You can get it down to 60 dB, and you can just go ahead and read this at your leisure when you want to take a look at this on our website. Or again, I'm going to give everybody the PDF that has all this information on there. It talks about a large 6 foot by 3 foot by 1 foot steel cabinet, bookshelves, again, edges wrapped with aluminum tape. They have a 60 dB, and think putting 1-gallon containers in these here, so that this augments the 50 to 60 dB suppression on that. So these containers are good because it contains heavy gauge steel sheet metal, and it's also very rugged. And of course, you can buy these all over the place. Warning number 3, and this has to do with solar panels. Some people have claimed that solar panels do not need protection from EMP pulses, but just thinking about it, that is totally wrong. Why? Because solar panels have a large conducting surface with the many solder points connecting the individual cells. They also have diodes, reverse current diodes, which can easily be destroyed by high voltages. When in use, they are connected to long cables that's connected to a controller, which all of this stuff acts as a large antenna. The controller has many electrical parts in it. So, of course, an EMP would absolutely take out solar panels and the charge controllers and inverters that this stuff is attached to. But the internet tells you differently, so just be forewarned. In order to have any hope of any protection, all the parts must be disconnected and put in one of those containers that we actually, let me do a page up here, put in one of these large containers for large storage. Now, this is the type of thing where you have a set of solar panels that are placed in these large metal containers, all wrapped up with aluminum tape, and you just don't touch it until after the EMP event. Then you can go ahead and bring it out and create your power. You'll be the only one on the block if you do that with power. Then the last but not least, we had the large microwave ovens, especially when you nest other Faraday cages and bags without aluminum tape. The microwave ovens themselves are about 40 dB. But again, with other Faraday bags, that you can increase that. And so they can be a solution, but you have to understand the limitations of the microwave oven. Okay, then you also have the small Ziploc Faraday Mylar bags that you find on the internet everywhere. They only have a suppression of 30 to 44 dB. So in and of themselves, they do not work for sensitive equipment. These have been tested. The ones that have been tested are very, very expensive that he tested out, that guarantee that your cell phone will be safe, your ham radio will be safe. That is not true. You have to have at least 2 bags layered together for that to happen. Then you have the cans with the zip type lids nested with Faraday bags without aluminum. There's, you can read that yourself. When you're nesting things seem to work out a lot better. Here's the same thing with aluminum tape. You can see the suppression was measured at 85 dB, which is perfect. Metal garbage cans. In and of themselves, they are lousy, but if you tape them up, then they become a very good suppression device by taping over all the holes, the handle connections, the lid. You can get, he measured it at 72 dB at 1.92 gigahertz. Without the aluminum tape, it drops to about 5 dB of signal suppression. So this is why things are fried. Ammo boxes, those are quite popular. The only problem is there's only about 24 dB of suppression, which means putting your ham radio in there will do you absolutely no good unless you put aluminum tape around all of the seams and the handle, and you also layer. Then you have the open-ended Mylar food bag storages that you can buy at the LDS Dry Pack. They're also pretty worthless in and of themselves unless you tape them up and you put multiple layers in. So your Faraday cage should become the primary storage place, and this is where it becomes really hard. In order for any of this stuff to really work, you actually have to have your devices in the Faraday cage. So on a day-to-day basis, starting today, let's say you had you created your Faraday cage, you have to keep those devices in that Faraday cage 24/7. You have to allow easy access. Wrong direction. Once an item is removed from the container, and if the EMP were to happen, the device that is out of the container will be destroyed, but you need to make sure that the lids are closed and sealed so that the remaining devices in the container are good. If an item is critical to one's life after an EMP event, then multiples of that item should be obtained and each stored in different Faraday cages. The probability of having all the devices destroyed goes down quite low if you have multiple Faraday cages, multiple devices. And here's something that's quite interesting. It would be wise to wait several days after an attack before opening any of the Faraday cages. And why is that? Why do you think one should wait?
Might be a follow-on attack.
And what are the probabilities of having a following attack?
I would say.
I'm sorry, we didn't hear you, Jan.
I would say they would be pretty high that there would be a follow-on attack after a day or two.
Extremely high, because the first attack would have destroyed the majority of devices out there. People who do have Faraday cages, the military stuff that does work, that are no longer protected, the military would have a less opportunity of protecting us after a second EMP, after the first EMP attack. So you can pretty much guarantee that you could have more than one EMP. So the problem is, how long do you wait? And so it's a crapshoot. Who knows? Faraday cages, which are stored in non-metallic, non-conductive surface such as wood or carpet, or on rubber wheels, can hold an electrical charge for some time following an event. So you have to bleed off that energy. So you would just use, oh yeah, and by the way, you don't want to touch it because you could get electrocuted hours after an EMP attack by touching your garbage can. So what do? You want to bleed that energy off using a grounding wire to ground. If you've ever worked with televisions, the old-time tubes, the CRTs, what's the first thing you do when you open up the back of the case? You want
Ground
to
out that flyback.
discharge. Yes, you want to ground out that capacitor because there's, I don't know how many thousands of volts there, but it's in the tens of thousands. And if you don't sacrifice your screwdriver, and that's why they use very large diameter screwdrivers, because there's a lot of current that goes through, and the same thing will happen to you if you touch a Faraday cage, a metallic, and you're grounded, you're going to feel it. While some of the Faraday cages can be stacked, this is important. If you stack your Faraday cages like your paint cans without having them inside of a larger container, then it increases the surface area. So instead of having a third of a meter, if you have three of them stacked together, you have a meter, which means you have 5,000 volts and you have issues. So you need to be careful on how you stack them, unless, of course, they're inside of another Faraday cage. So that's important to understand. So here's the deal. You too can measure the effectiveness of your Faraday cages, all the way down to mil standard 188, 125. The problem is, if you were to do it right now, it's very expensive. None of us probably can afford the equipment. Without proper controls, the results are erratic and inaccurate. And like I mentioned, the cost is probably out of the reach. So what do? Well, an inexpensive way is to obtain two containers that have a known dB suppression level over the required frequency range and use these as a standard. This is exactly how the author of this did, and that's how he was able to do a lot of the tests that he did. You have to have a constant signal source, and the signal has to be stable above 1.5 gigahertz, which has been identified by the military as the upper bound of the EMP frequency. And a physical test location is needed, which will remain constant. And that means humidity, temperature, a few other things that come into play there. And it must be sufficient large enough to do both, do your source and your comparison. And I'm not going to go into how to do that, but he actually goes in to how to build your own measurement device. For me, I'm going to just go with what he has done, because you want to talk about people who are anal. This guy is anal. He went to school at MIT. He knows what he's talking about. He's been doing this all his life. And all the information that I've ever seen on the internet compared to the information that he has done, that he has personally tested, I'm going to go with him every day and twice on Sunday. So with that, does anybody have any questions?
So are you going to build a fancy schmancy Faraday safe environment up at your ranch? How
I'm going,
preppery are you?
yeah, I think it is, I have enough ham radios to permanently store radios and batteries uh, in. I like those paint cans. Those are probably the best, and most of my radio will fit in that. I do need. I have the paint cans. I had some mylar insulation material. I need to actually get more. Actually, if we as a club buy like a thousand bags that will actually go inside of a gallon paint can, they're pink electrostatic um, uh, insulation material that people will put their electronic boards in. If you've ever worked at a computer center and you have things that are delivered in a mainframe, they're all delivered in this pink stuff. That they have the same thing for the large pails, for the large 55-gallon drums, for the 5-gallon drums, and for the 1-gallon drums. That that stuff is very, very good for the insulation because you have to have all three. You have to have the good sealed can, the um, oh, and by the way, one thing that he also talks about in his write-up, it's multiple pages, by the way, is the thickness of the metal also counts. So one thing good about those cans are at a gauge where it's perfect. Uh, so using a mallet to pound the lid on with your radio in there inside of uh, the insulator, the insulated bag, I think that's everybody can do. And this is where a couple Baofangs are going to go in. My charges are going to go in there. Anything that will make that device work needs to go in there. Seal the can up and put it in storage. You know, so
Now we need to have a presentation on emergency power and some way to retain that power after an event like this, right? Because
yeah,
don't have your
when
solar
I
panels safely stashed away, then you're going to have this equipment, but when your batteries run down, you're kind of out of luck, right? So
exactly, and you're going to need to understand that everything I have in this long storage stuff, obviously my batteries are not going to be attached to the radio; they're going to be separated.
Right.
But they're going to be probably completely dead because I'm not going to be
take them
using
out
these
and charge them all
radios,
the time,
right?
right?
Yeah, exactly. So, so yes, I need to dedicate a even just a suitcase type of solar panels and charge controller and batteries. Nobody know. Well, I can't remember what JT said about batteries. Batteries should be okay because there's nothing to actually. The plates are separated anyway. So your car batteries and stuff should be okay after an EMP.
It's just the electronics that would fail.
Just
right?
the electronics, yeah.
So if you have
yeah.
a car from the 70s that doesn't have electronic ignition, it might even still work.
If you got cars with points on, you're good to go. Yep, there's nothing to fry on those. If you look at the a microprocessor and you see how fine those wires are, all that stuff gets vaporized. Uh, that's the problem with the E1 pulse. This is the problem with having, so this is why EMP is so dangerous. When it happens, all of our hospitals are powered by diesel generators, right? For emergency power. Guess what?
Start them.
They'll never start. It's all controlled by electronics.
Yep.
So this is why the commission on the electromagnetic pulse that was brought to Congress said that within the first year, 90% of the population of the U.S. is gone. Within the first hour, millions of people are dead. That this is why the EMPs are so doggone scary, which is probably, we talk about EMPs, we talk about something so drastic. I'm not sure that we would ever get one. Preppers are just that. They prep
You can
for
spend
that.
as much as you want on prepping.
Right,
I mean,
right, exactly. So my belief is I think it's fine to take some radios and just in case type of stuff, but I'm not going to live in my basement wearing a Mylar bag around me.
tinfoil hat.
Yeah, and a aluminum foil lined hat to to live my life. I'm not going to do that. So everybody has to decide for themselves what to do. This presentation was built around if you want to protect something from an EMP,
This is what you have to do.
there's a way to do it. Yep. And one of the things I liked about JT again, he talked about being thorough. This presentation was kind of hard because he was so doggone thorough, and every contingency he thought about. He worked closely with the reports on the congressional report, and he went through each one of those. And during the time that I was with him, it was incredible. He just the vast knowledge that guy had, and how he was able to do all of this stuff is just boggles the mind. So,
I remember reading a document years ago. It was a military document about preparing or designing a radio facility to withstand an EMP. I read this way before I got into ham radio, so more than 20 years
right,
ago. But one of the things that was a factor was it had to be able to be operating even during the event. And how do you bring signals in and take signals out? And they used waveguides, and they used like baffled doorways where there wasn't a clear straight path through. You had to like go in through like an airlock type door to get inside, and only one
right,
door could be open at a time and that kind of thing. And some of the stuff that they plan for and they think about in the military world just blows your mind when you think about it. And you think, wow, how much of that would I even consider doing, even if I had the means to do it?
right,
Who am I going to talk to on the radio after an EMP anyway? So
right, exactly.
it's going to be more important for me to figure out how I'm going to get food and water and sanitation and whatever else I'm going to be needing.
Right.
So I don't know. It's just one of those things. Obviously, we have grown accustomed to our comforts in this country, and the thought of not having them makes us cry. But that's something to think about.
Well, during the last presentation, if you recall, I talked about CMEs, and
CMEs are not unlikely, right? I mean, we just missed one a couple of weeks ago.
We are more likely to get a direct head-on 1857 event than the EMP, and it's easy to protect against a CME. Unplug everything. As long as you're not connected to the grid, you're good. The induced voltages are nothing like an E1 or an E2 pulse. It's the E1 pulse is the killer for EMP, but a CME, that is more likely to happen, and even a CME can really plus we have hours to prepare for a CME. And if a direct head-on CME would happen, there would be all kinds of radio emergency broadcasts saying, we got a CME coming our way, a Carrington event type of thing. That we can do. That we can plan for. But an EMP, you have no, unless you happen to be in where the intercontinental ballistic missile, you can see the tail going over you. You know, you're not going to know.
I grew up on a missile base, and that was something that we were taught about. Was, you know, if you see something that looks like this from, I mean, the missiles were up to 150 miles away from the base, but still, you see
Yeah.
something like this out in the horizon, it's pretty much over, you know. So
Yeah,
make your peace. And
that's right.
I mean, we had fallout facilities and things like that. We even had a blockhouse there. We had one of the Sage blockhouses, and that thing could withstand it, I believe.
Mm-hmm.
But you know, very few people were authorized to go in there, so that was a thing to consider. You know, the mission comes first, the families come last. So we had to be aware of that and think about that on a daily basis when I was growing up. And you know, you think about that now, and our risk profile is so much lower now than it was back in the 70s and 80s. That we really, sometimes I think we worry too much about things that we shouldn't. But it never hurts to be prepared for what might happen, right? So,
Right. You know, the difference between a CME and the EMP, you know, I would put 80% of my efforts in protecting myself against the CME and 5% against the EMP, because there's, you know, it is what it is. So, and does anybody have any questions on Faraday cages? I think it's funny that the internet is just, if you go online and say, okay, how do I build a Faraday cage? Do that right now, and you'll see the exact things that you've been warned against today. Neil, you have a question?
Yeah, I just watched one just the other day with the ham radio not the concept. It's a redheaded guy.
Yeah.
and radio crash
But-
course.
Yeah, he just did one with like a little, I don't know, if like a 5-gallon or 6-gallon a can, you know, aluminum can. So I was like, well, okay, that, you know, and he did warn that it has to be, you know, sealed off. No air can get in.
Right.
If any air could get in, it was going to be done. But
Yep.
yeah, I think I like the paint can a lot better.
Yeah. Back when he first gave this presentation years ago, 2014, of course, I was working with him from let's see, let me think about this. I was working with him for about 5 years because he was with a Provident Living class that I was involved with. And we learned, oh my goodness, so much about sanitation and being prepared against anything. And by the way, I have a great sanitation presentation that that's from that class. That, you know, in an event where society goes crazy, like a EMP, you know, I'm heading off to my property, just so you know, and because the people, my neighbors, they don't know how to deal with their sanitation. You know, if the electrical grid goes down, which is what could happen during a CME, you know, it's all over. And so, you know, there's ways to deal with that. And if we're not all dealing with it the same way, then it becomes very dangerous. So, you know, one of the things that our club has started to do is kind of get into personal preparedness. And Ragnar last week suggested is going to donate P38 and P51 can openers. I have right here a 96-hour preparedness kit checklist of things to put in your 96-hour kit. This is based on the Safe Neighborhood program. I have Joey from Murray City. He's going to be giving us some things. And it's been decided that we are going to have we're just not going to give you the packet with all the stuff. That would be way too easy. What we're going to do is, what do you call that, Jan or Ragnar?
Geocache.
Geocache. Yes, thank you. We're going to have a geocache system set up where you have to, by coordinates, find it yourself. And so I'm working with Joey to find that very special place, and be ready to get instructions on the coordinates of a packet that we're going to make for everybody. And I hope, I think this, maybe I'm wrong. Is there anybody who does not think that ham radio is not a part of the personal preparedness effort?
Well, we talk about emergency communications all the time, and if you're in an emergency situation, being able to communicate allows you to take advantage of other resources that you may otherwise not be able to get at. So I think it's a crucial part, and I recommend to everybody that I talk to about emergency preparedness that they should get a license for their ham radio and learn how to use it. So
yeah. Yep. Is it just Jan and I that agree with that, or do other people agree with that?
no, it's just you and me, Dan.
I can see Neil. Neil,
I'm awake.
I push that all the time to get ham radio license for communication purposes. Anybody to do it, but I push for
Head's
it.
still there. Wow.
Say again.
Your head's still there, he says.
So, man, all of a sudden we got Bob and Sam. Oh, Sam, welcome back. So, with that, I think let's go ahead and end tonight's class. Thanks
Right on.
everybody for joining.
I'm going to stop the recording.
Okay.